So there's a question about disproportionation reactions. And you can get hung up on all these subcategories of reactions, which is fine. You know, for example, let's look at this. What do you call this reaction? You call it decomposition or a disproportionation reaction. This is a classic example of disproportionation reaction. But, you know, what do you call this reaction? Well, most reactions are synthesis because they're trying to make stuff. What would you call this one? Do you call this reaction reverse of decomposition? Do you call it the reverse of a disproportionation reaction? Well, both of those are true, right? It is the reverse of a decomposition. It is the reverse of a disproportionation. This is the reverse of a disproportionation reaction. So are you going to tell everybody, oh, this is the reverse of a disproportionation reaction? No, you just tell them it's a... Well, you know, before you get into all the subcategories, just learn the main categories, right? If you learn the main categories, then you can subdivide it however you want, you know, single replacement, whatever you want to do. But just learn the main categories, much easier. The main category, both of these reactions are redox reactions. So just call them redox reactions. You don't have to get hung up on subdivisions and subcategories yet. You know, if you want to specialize in a certain type of reaction, go ahead and do that. You know, but not now.
Yeah, the homework is one called decomposition right?
Yeah.
And it's a solid form. Would that also be redox?
Yes, you're right. Right. You can easily, in Chem 1A, you should have done this. You know, you probably had to identify redox. This is a redox reaction, this is not a redox reaction. Very simple way to identify redox reactions, and that is, in a redox reaction, the oxidation states change. In acid-base and metathesis, they do not change. And so just redox reactions, you see a change.
But do we always have to check the oxidation states?
Do you always have to check the oxidation states? No, well, you know, I don't know. I don't know if I do this subconsciously or not. But if I see a reaction like this, then I automatically know this is redox because I see there's got to be a change in oxidation state because this is an element. All elements in the elemental form are going to have zero, and these are compounds, so there's got to be a redox. You know, I don't check the oxidation. I don't actually calculate it. I just automatically, I look at that and I see that's got to be a redox reaction, right? No other, can't be acid-base or metathesis, it's got to be redox, you know. And so, yeah, I guess I always check because you know, I'm so familiar with the oxidation states of these things, I can just see it right off, right? But if you're not so familiar, then maybe it's a good idea to check the oxidation states. You don't have to check every single one, you know, just what you suspect. Maybe I suspect this to be a redox reaction, then just look at, you know, maybe I suspect this to be a redox reaction. Well, just look at the key, you know. I would just look at carbon right here. Did carbon's oxidation state change?
No.
No, it went from +4 to +4. This is not a redox reaction. This is a metathesis. This is acid-base, you know. If you say decomposition, then I'm going to ask you, is it redox decomposition or acid-base decomposition? Because decomposition, or is it redox, acid-base, or metathesis wouldn't have a decomposition, but I could ask you that. And then you have to explain it to me. Because decomposition, there's two subcategories of decomposition, acid-base decomposition and redox decomposition. So that's why I don't like this decomposition as a subcategory, because I have to ask you a follow-up question right after that. I don't want to. Right? This is just acid-base. Now, it is a decomposition. I mean, by carbonic acid decomposes. Everybody should know that. But as far as categorizing the reaction, it would be an acid-base reaction. All right, any other questions on reactions? Uh-huh.
Specifically, is it Bronsted loud?
This one?
Yeah.
You can answer that. How do you know that? What is the definition of Bronsted acid-base reaction? Give me a one sentence or one phrase definition of Bronsted acid-base reaction.
It could donate a proton or a
Yeah. Okay, so what is the proton donor? What is the proton acceptor here? No, it's not, right? I mean, not really, because it's more than a proton mix, right? And so this would not be a Bronsted acid-base reaction. This is, in a Bronsted acid-base reaction, very simple. One species loses the H, one species gains the H, and that's it. This is more complicated because there's O transfer also. Do you see that? And so that means this is not a Bronsted acid-base. Bronsted acid-base should be very simple to recognize, very simple to predict. For example, we can make a prediction. Could H3O plus be a Bronsted base? Is it possible it's amphoteric? And so it's very simple because the Bronsted base is a proton donor. And so we get H4O2 plus. H4O2 plus, is that possible? Well, you could try to draw the Lewis structure, Try to draw the Lewis structure, so something like this. You go, oh yeah. It's a formal charge on oxygen. Does that look like a good structure to you? Well, yeah, it's got an octet. Does it look like a good structure to you?
No.
Why not?
The formal charge is too high.
It has a fairly high formal charge. Now, plus two formal charges have to be stabilized in some way. The formal charge is pretty high. And so, that can go on. If you go to H5O3 plus, there's no electrons born to bond. There's some structures that are clearly unstable. This would be clearly unstable. Maybe. It doesn't look good. This is why we say, hydronium's. Yeah. Whereas hydroxide, is it possible for hydroxide to act as an acid? Well, this one, let's put a question mark under this one. Maybe you form unstable stuff. Hydroxide, if it acts as an acid, Bronsted acid, it just loses an H+. Is that possible? Well, it's possible because we recognize this ion. This ion is oxide, which occurs in many, many compounds. Whereas something like this, we don't recognize, and it's hard to stabilize that 2+. And so here's, if you have somebody, who doesn't understand anything about chemistry, and they go, well, that's a 2-, that's a 2+, here you have to have some kind of, some kind of basis, some kind of experience to, a lot of people, they have 30 years of experience, fixing cars or whatever else, 30 years of experience doing this. There's a lot to be said about experience because they pick up little facts here and there, little observations here and there. The same thing in chemistry. You talk to a chemist, a synthetic chemist who's been making things for 30 years, they have lots of little facts they pick up 30 years, What the purpose of Chem 1B is to cram, because I learned from, very seasoned synthetic chemists, you learn a lot of stuff. Then Chem 1A and 1B, you try to cram that in, there's no reason that you can't learn it much more quickly than they did, There's, in fact, this whole metathesis, acid-base, redox subcategories, that isn't mine, That's from one of my synthetic. Actually, there's a book that divides it into that too. But a lot of people ask me, where can I find it? Well, you're gonna have to buy it. You're gonna have to buy a graduate level, professional level book. people who actually work doing this type of stuff, not people, you know, like the textbook person's probably not a synthetic chemist, right? Doesn't pick up. That's why they come up with these categories like this. Well, anyway, let's move on to. Are there any other questions about reactions? Uh huh.
Can we do have oxidation?
Oxidation.
Yeah, oxidation. But there is on the bromide, it's like number 5.
Tell me what number 5 is involved.
Sodium is first, added to aqueous potassium bromide.
Okay. Sodium Na, solid, liquid, gas, AQ. Aqueous. Now, aqueous potassium bromide has lots of water around. And so that means, you know, if sodium is soluble in water, we could write it solid or AQ, you know? But anyway, this one, this particular reaction, I like this because it should be simple. It falls into the A plus BX, you know, single replacement form, right? A plus BX yields B plus AX. B is potassium, sodium bromide. Sodium bromide soluble, all sodium salts are soluble. Potassium should be a solid, it's metal. Is this what you get? I'll tell you, you might not have gotten this, but maybe at least every semester, at least maybe 10% or 15% of the class gets this. Sometimes it's been even greater, 20% of the class gets this.
Oh, I got the reaction, but they, when I looked it up, and they said we have to do the Na, and we're gonna add electrons here, and K, we're gonna add electrons on the other side. So do we have to do every step about it, or just we have to do that like if base and acid, that's it?
Well, remember when I was talking about single replacement, you have to memorize patterns, and then you look for those patterns. But sometimes when you look for those patterns, it tricks you, like this problem. This particular problem was meant to see if you fall into just strictly pattern recognition. You know, I remember I was talking to one student, and, you know, one student learned stoichiometry. Stoichiometry is always 2 steps, you know, step 1, you know, gram to mole, step 2, mole to mole, something like that. It's not always. If you get stuck in patterns, then you need to see a lot of different patterns. You know, because there are going to be patterns. In Chem 4, you're safe because they'll never throw a pattern out there that doesn't fit, you know. In Chem 1A and Chem 1B, then we're going to throw patterns out there that don't fit the recognized patterns for you too. This is wrong, by the way. Totally wrong.
No reaction.
No, violent reaction. This is a violent reaction, but that's the wrong reaction. It doesn't react, sodium doesn't react with sodium bromide. This is a potentially explosive reaction.
You need an explosion shield.
You should have an explosion shield. Once I did this reaction, and a little molten fireball of sodium went flying up and hit my arm.
Ow.
I think I still have the burn from it. But I had a little molten sodium fireball right there. Another person did this reaction and ended up burning down the lab. This is a very famous story. The research labs at UCSB are shared between 2 students. So one student poured acetone down the sink. used to be okay. Well, actually, it used to be okay. Acetone has 3 carbons. And now 3 carbons down the sink is not okay. 2 carbons is okay. So ethanol, and things with 2 carbons is okay. Anyway, this person poured acetone down the sink and didn't flush it with water. And then he comes along, he has just a tiny bit of sodium. And sodium is very dangerous. So he saw a puddle of water there. Puddle of water, thought, oh, I'll just throw it in the water and it'll flash and burn, you know? But it turned out it wasn't a puddle of water, it was a puddle of water and acetone mixed together. Big flame, burnt down the lab. And, you should have been able to smell, and you got to flush it. You never know. If you're working with other people in the lab, you got to just watch out, because what they're thinking and what you're thinking might be totally different. One time I was sharing an office, and I had a coffee mug there, and my lab mate was looking for a beaker to put in some samples in these long, thin tubes. And so I come in and I see my coffee mugs filled with samples. And I asked my lab mate, what are those? Oh, those are just thallium samples. Have you heard of thallium? Thallium has been used to murder people as a heavy metal. People used to poison in the past, if you read mystery stories and that kind of stuff. And there are cases, documented cases of people. So I'm thinking, oh, my lab partner's trying to murder me. No, lab partner, what's the big deal? They're sealed in glass. There's no risk of thallium. And you know what I did with that? I threw it away. And, just to be safe. It's a heavy metal. So So some people, they don't, lead. What's a little bit of lead? It'll just toughen you up or something like that. It's just like. I just couldn't believe it. Anyway, and then I realized, do you want that person making your decisions? No, I don't. I think. Oh, anyway, going back to this. This is I see this. This is going to be a very violent reaction. And this is, what do you suspect? Single replacement? No. Well, yes. Single replacement, but I don't do single replacement unless you've memorized all the exceptions. Have you memorized all the exceptions to single replacement? Then don't do it. When you memorize them, then go ahead and use it. But in Chem 4, it's easy. You don't have to memorize any exceptions because every reaction they give you is going to work, right? In Chem 1A, we don't want to have to limit the number of reactions that we give you, so we want to broaden it. But eventually, the number of exceptions that you have to learn and memorize grows too big. It's a hassle. It's not even worth it. And so rather than doing that, we use a different method. What is the method we use instead of single replacement? The half reactions using the half reaction chart or the redox chart. And so we use the chart method. The chart method, we just inventoried sodium solid, potassium ions, bromide ions, and water. Potassium ions are a reducing agent on the chart. Sodium is a reducing agent. Potassium ions are oxidizer. Bromide's a reducer. Water is both an oxidizer and a reducer. When you go through the chart, the strongest oxidizer is not potassium. That single replacement would have you believe is potassium. The strongest oxidizer in this mix is water. And the strongest reducer is sodium. And so have you ever seen sodium react with water?
Yeah.
Yeah, well, I showed this, but I trying to show this. Let's see. There used to be a better video on this. But I don't know what happened to it. Yes.
Why is water a stronger oxidating agent than...
We don't care. We don't care at this phase. At this phase, you just use the chart. The chart says water is better. And so don't question the chart. The chart is experimental fact. And since it's experimental fact, we'll just use it as fact. Now, that's a great question. Why? So my initial answer is, to pass this course, you say because the chart tells you, right? To do well in this course, then you ask, okay, why would water be a better oxidizer, right? And there we would need, we would need a two-pronged kind of deal, where we think about chemical reactions. When we think about the driving force for chemical reactions, we just want to learn. Because first we got to get some kind of, like you said, some kind of reference point, or some kind of basis, factual knowledge, basic factual knowledge down. And then later on, we try to understand theory, right, and experiment. And so a lot of people say, we don't need any memorization, right? You don't need any memorization because we could all figure this out theoretically, And so tell me why potassium ions are a weaker oxidizer than water theoretically without doing any memorization. Well, the chart says so, but now we want to get in deeper because, in the scientific method, okay, we have, scientific method deals with observation. We got all these observations which lead to these patterns or trends. And then from these patterns, we can generate laws. And so let's go to the ideal gas law. Did you ever question why the ideal gas law said that? For example, the ideal gas law says that if you double the Kelvin temperature, the volume should double. And then did you ever ask why? Or did you just say, that's what the ideal gas law told me? Right? You just said, well, that's what the ideal gas law tells me, right? Well, saying that is just the same as saying, well, that's what the chart says. Because the ideal gas law is just some mathematical function that fits this pattern. But tell me the theory. How could you derive the ideal gas law theoretically from the theory of chemistry, right? Have you ever had to do that? Or have you ever had to argue why the ideal gas law behaves the way it behaves? Right? No. You just use it, right? And these are observations that we use, but the observations are just in a mathematical form. That's it, But that's not enough, right? Then you start thinking, well, why is water a better oxidizer than potassium ions? Well, it has to do with structure and composition, right? And so then we start looking, deeper into it. The whole thing with the ideal gas law, if you were to stop here, then all you know is just that, just some pattern. That's all. You just learn some pattern based on observations. But really what we want is we want a deeper understanding of these things. And the deeper understanding is a hypothesis. And the deepest, hypothesis is a tentative theory. The deepest understanding is theory, Why do gases behave this way? Why does the ideal gas law predict that the volume goes to zero? How can we have zero volume? Is that even, volume is 0 liters. Well, 0 liters is nothing. What's going on with the ideal gas law, right? There's something wrong with the ideal gas law. Yes, there's something wrong with the ideal gas law. Because it's for ideal. This is why we call it ideal. It's not real. Anyway, well, we can look at the theory. The theory gets into that. And so what we're doing is, if you want to understand why water is a better oxidizer than potassium ions, then we got to look at it, more deeply. Right now we're just looking at the patterns. These are factual patterns. Can come up with the law of oxidizing agent strength. The higher up it is, the stronger it is. Some pattern it is. Or the lower down it is, the stronger it is. Whatever. That would be the law. Okay, but for us, we want to delve deeper, and delving deeper is we look at the structure and the properties. What about the structure? What about the composition that gives it this property? That's what scientists do. Every time I ask, in Chem 1A I ask this question because we try to drill down the scientific method. One of our student learning outcomes, these SLOs, these SLOs are mandated by the state and maybe the federal government. But one of the outcomes that you should get from Chem 1A is that you should know the scientific method. And so often I get this from the scientific method, which is fine because they do this in biology. You know, in biology they say, oh, you pose a question and then you make some kind of hypothesis and then you test it, you know. Well, yeah, that's fine. Maybe that's what biologists do, but everybody I know did this. You know, they take down lots of observations and they look for patterns. And then they try to understand this structurally, you know, that composition structure. Get more insight into why things behave the way they behave. So for example, you're looking for drugs. You know, why does this drug have this property? Well, it has to do with its composition and structure. And so you try to nail that down, you try to understand it, and then try to design new drugs that have similar structures or like composition, maybe not as toxic, you know? There's the whole thing with aspirin. Aspirin used to be a heck of a lot more toxic, right? Aspirin used to be an acid, and then they said, okay, let's get rid of the acid proton. And so what they did was they replaced the acid proton with a methyl, or I think it's a methyl. They put a methyl group instead of the acid proton. And what that did was it dramatically reduced the side effects of aspirin. And so it wouldn't kill your stomach or eat up the lining as bad. It still does, obviously, but not nearly as bad as once did. And so that comes from this whole structural, you know, theoretical analysis. And so they converted an acid into what they call in organic chemistry an ester. But that's a good question. But a lot of people, they get caught up, they get hung up. You know, they get hung up, and I know. How do I know they get hung up? How do I know they're overthinking? Because they leave the page blank. They can't even start it, you know?
But they can't even start what?
They can't even start a problem like that. They just leave it blank because they're just overwhelmed. The thing is, you don't get overwhelmed because you build up in steps. The first step is just be able to use it. Don't think about it, just use it, you know? This is why I say an elementary school kid won't get hung up because they'll oh, this one's higher, that one's lower, this one, you know, that kind of thing. Right? They aren't going to think, oh, why is that a stronger oxidizer? Can water be an oxidizer? You know, just look it up, right? A lot of people start thinking, wow, this is overwhelming. I'm getting overwhelmed because this is too hard. You know, why is water a more powerful oxidizer than potassium ion? You need to ponder that point, right? But you don't. You don't. This is why I always say this. This method is very easy. People are always asking me, where can I find it in the book? Well, unfortunately, you can't find it in the book. Well, if it's not in the book, it's too complicated to learn. And it's not fair that you're asking. You know how many times I've gotten that? It's not fair. This chart method is not fair. It's not in the book. It's too hard. Yes. This is why I'm not addressing this to everybody. Just, you know, if you're thinking it's hard, it's not hard. You just got to try it a few times and don't think about it. Just use the chart.
No, I just tend to think about it deeply. That's all.
No, I'm not talking about you. I'm just saying that's good that you're thinking about it deeply, right? And the thing is, once you see it enough times, you do 10, 100 of these, then you get bored and you start thinking, you know, I need to know a little bit more. So I want to, you know, and I see these patterns come up. You do things over and over, you start to recognize these patterns, right?
Mm-hmm.
And then you start wanting to learn more. That's the point where it comes, you know? But if you try to do everything at once, then it might be information overload. Because there are a lot of patterns in there, you know? I already talked about the single replacement, but there are others, right? And how are they related? It's like this, you know, why is this? Well, we started talking about it. In chemical reactions, we have the driving force, so just learn the simple driving force, right? And then later on, we're gonna start thinking, you know, when we look at a reaction, what makes this reactant a better reactant than this reactant? In other words, what makes this acid stronger than this acid? Well, there are multiple factors there, multiple patterns, right? Bond strength, polarity, stability of the product. You know, if somebody were to ask me right away, you know, I'd tell them, you know, this makes an awful product. The product of this is, if this were the oxidizer, the product of this would be potassium metal.
Which would happen?
Potassium metal's totally unstable in water. I showed this earlier, but there used to be a better video of this without this little commentary at the end. But anyway, this is the only one. Since they deleted the other, I guess they deleted the best one off YouTube, unfortunately. The one that had just the original and didn't add this modern commentary, which I'm going to cut out.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surface chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions.
Wow. Really close.
Still reacting way up at the top of that cloud?
That cloud, you don't want to inhale that cloud. It's sodium hydroxide.
Is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Wow.
Okay, so the reaction isn't between, so if you did this, you would have gotten NR, because potassium is more active than sodium. But no, NR is the wrong answer. And so like I said, in Chem 1A, when I give this, I don't always give this, but when I give this about, a bunch of people will say no reaction.
Okay then, but if NR is the wrong answer, what's the right answer?
If NR is the wrong answer, what's the right answer? The right answer is you just follow the method. Following the method is this. I don't have to know what sodium does. I just copy it off the chart. I just look, sodium solid goes to sodium plus an electron. Right? Water. I just copy this off the chart. Water. And I just look it up. Water, actually, I don't, I gotta look. Your chart is a little different than their chart up there. But water plus 2 electrons is gonna yield. What does it yield? See, I don't need to know, because what do? I just go to the chart and just copy it off the chart. What does water do? It's going to form hydrogen gas, right? And hydroxide. It's 2 hydroxides. We got to make sure this is balanced. Is that right? Yeah. And then what do? I just add them up. You just need to multiply this by 2. So I get 2 sodium solids plus 2 H2O liquids. The electrons must cancel. You've got electrons left over, something's wrong. 2 sodium ions, hydrogen gas, plus 2 hydroxide. This is what causes the explosion. It's not this reaction technically, it's the product of this reaction. The product of this reaction combines with air, right? Hydrogen gas plus O2 and air yields a big explosion. So it's the second reaction that causes the flames and the explosion. First reaction violently produces hydrogen. This is highly exothermic. It gives off a lot of heat, and so this energy that it's given off is enough to ignite the hydrogen. You don't need You don't need a spark. Did they use a spark to ignite the hydrogen? No. It was just enough energy was produced in this that it ignited it. You just need collisions, that's all. A hot surface.
So if you see future single replacement reactions, just follow the method or
Yeah.
write NR.
No, you don't write NR, but just follow the method. My point of all this, and this is what you should have in your notes, and the point of this is just forget the single replacement. I didn't even tell you all the exceptions of the single replacement because I don't want to. It's a waste of time. Just forget. Some reactions, if you have a driving force, if you're good at single replacement, you can just look at it. Oh, that's a single replacement, there's a driving force. If it's a single replacement with a driving force, go ahead and use it, right? But if you're getting no reaction, then you've got to be careful, because you might be missing the reaction. We already did 2 that you would have missed. Copper with nitric and sodium with sodium bromide would have been 2 that could have potentially missed. You've done that. So we don't have to understand everything theoretically, We could just understand it based on the pattern. We could use these patterns to make predictions, right? Because these patterns are based on factual evidence. And this is the pattern we have here. We could call this the law of the redox. Rather than call it the chart method, I'm going to call it the law of redox. Because then you might want to understand the law of redox theoretically. Then you're going to have to understand structure. So not everything we need to understand theoretically. There's some people that have to understand everything theoretically.
Professor?
Yeah.
What would be the driving force for hydrogen and oxygen gas?
Hydrogen and oxygen gas
To water.
to water? Okay, what's a better reducing agent? Hydrogen or water? What's a better oxidizing agent? Oxygen or water? Oxygen. So there you wouldn't even need the chart. You just say you're going from stronger to weaker. But water is the same. So water acts both as the oxidizer and the reducer. And so this is why we start looking at things structurally. We start looking at things structurally because that's going to tell us the active sites. We were looking at active sites in terms of acid and base. In terms of acid and base, hydrogen would be the acid sites, oxygen would be the base sites, and water is amphoteric, right? In terms of redox, we look at it based on the atoms. So hydrogen's +1, oxygen's -2, hydrogen's +1. And so the hydrogen in water will be the oxidizer, but it's just water. Hydrogen in water is not a great oxidizer. Hydrogen in acid is a better oxidizer, right? The oxygen in water is the reducer, and so this particular compound can do both. It could be an oxidizer, it could be a reducer, and in certain scenarios, in certain reactions, it's both the oxidizer and the reducer. It's just it's like this is different. This is different than this. So, for example, hydrogen peroxide is both an oxidizer and reducer. Did you see it on both sides of the chart? A lot of people never look at the chart. And so they think, oh, hydrogen peroxide is only an oxidizer. But no, it's not just an oxidizer. It can be a reducer too. Did you guys see it on both sides of the chart? Well, I'll tell you, a lot of people, how many people actually looked at all the entries in the chart? Just a couple of people. You people will be ahead of everybody else. This is one of the things I learned when I transferred to UCLA. I never looked at the chart. I just looked for what I needed. But, the best thing is you look at all the entries, and then every once in a while you just refresh your memory. This way, there are certain things that go into your subconscious. You might not actually remember it because you don't actually memorize it. You never memorize it. But when you read the entries, let's say a few times, and something goes into your subconscious, and then you get a problem, let's say on a test or something, and it's something you don't recognize, but something here clicks because your subconscious remembers it or something, and you saw it before. And so people who actually read the entries they say, this is something I learned from a professor there at UCLA. He said, you know, people who actually read the entries are really a step ahead of everybody else. You know? This is important because at UCLA, you know how many pre-med students are at UCLA? A lot. And they all want to go to UCLA med school. And they're all going to do what it takes to get in there. So it's hyper competitive there. And so just to keep your head above water, you have to be hyper competitive too, otherwise you sink. But even though you might not like this hyper competitiveness, you know, a lot of people don't, so a lot of people do. But it was okay, you know. But this is very different because this is an oxidizer and reducer based on different things. You know, if you were to use the pattern for water, you'd say, in water, the hydrogen was the oxidizer, you know, like in the last reaction, or in this reaction here. The hydrogen in water is the oxidizer. It's going from +1 to 0. It's taking an electron from sodium. So the hydrogen in water is taking an electron from sodium and creating hydrogen gas, which explodes. The hydrogen peroxide is quite a bit different because it's not the hydrogen. If you look at the reaction in the redox chart, the hydrogen's oxidation state stays the same. And so in this case, this atom can go either way. This atom can be an oxidizer. If it's an oxidizer, it goes from -1 to -2. And so this is when hydrogen peroxide acts as an oxidizer. If this is a reducer, this one goes from -1 to 0, creates oxygen gas. And so this same atom can go either way. The reason it can go either ways is because it's in the kind of in the middle of the range. You know, things in the middle of the range like carbon. You know, carbon, the element, excuse me. Carbon, the element, can both be an oxidizer or it could be a reducer. Carbon can be an oxidizer and form carbides, like, you know, silicon carbide and other things, you know, carbides. Or it can be reducer and form things like CO2 or carbon monoxide, you know, that kind of thing. And so this is different than the water scenario, but you understand these things because you pick up these little things as you go along, you know, these little facts about structure and properties, and then you catalog those in your subconscious. And hopefully all this, and then your subconscious gets to work at making these connections, you know, putting these connections together and trying to formulate a better understanding of structure and properties. Okay, so this one you just complete it using the chart method, that's it. Any other questions? I didn't finish it, but it's okay? You guys can figure out the oxidizer or reducer, or you want me to finish it? Finish it? I was hoping you wouldn't say that. Hoping you wouldn't say that because I'm running behind, but it's all right. Finish it. So the reaction was between sodium and water. So we add up the two half reactions. And this is what we get. 2 sodium solids plus 2 water. You know, hydrogen. Actually, let's write this. 2 sodium plus 2 hydrogen gas. 2 OH minus. Then we look for a driving force. So here, this is our reducing agent, here's our oxidizing agent. The reason why, you know, you go, well, 2 sodium ions and 2 hydroxides, what's that? That's 2 NaOH, right? 2 sodium hydroxides. But I'm going to write them separate. The reason I'm going to write them separate is because our reducing agent on the product side is hydrogen with hydroxide, and our oxidizing agent is just sodium ions. So I split up the sodium and the hydroxide so I can have a reducing agent like this. Note that this is going to be in net ionic form. When you do the chart method, you always end up with a net ionic equation. So you don't have to do the complete equation in ionic. You just leave it as a net ionic. How did I assign these? Is the easiest place to assign this here? How did I know hydrogen and hydroxide combined is my reducing agent? Somebody tell me that. Did I just have that memorized? Where did I get that from?
Half
the half reactions. It's difficult. If you were to just look at the net ionic equation, and would you have been able to sign this like this easily? No, the reason I was able to sign it easily is because of the half reaction. I don't assign it at this phase. I assign it during the half reaction phase. During the half reaction phase, it was 2H2O plus 2 electrons yields H2 gas plus 2 hydroxides. In the half reaction phase, here's my oxidizer. Therefore, the conjugate reducer is this. And so I knew that from the half reaction. I erased the half reaction so you wouldn't see that. But with the half reaction written there, it's easy to see that the conjugate reducer is hydrogen and hydroxide, right? And so this is how I signed this one so quickly. And then we compare the strengths. Well, it turns out sodium is a strong reducer. And how did I know that? I didn't memorize that. I just looked at the chart, and the chart should tell you easily, you know. This is why I say elementary school student can just see this one's higher, that one's lower, therefore this one's stronger. As far as oxidizers go, water is a stronger oxidizer than sodium. You know, the thing that could trip up an elementary school student is if you give them a different kind of chart. Now, if you take a look at our chart there, does our chart look like the chart in the book? It's reversed. That chart up there has the activity series at the top left. Do you see that? Lithium, etc. And this one has rubidium. But if you look at that, yeah, it's totally reversed. That would trip up in elementary, but you should know it because you should know that lithium and fluorine are the most powerful agents. Okay. All right, other questions? Uh-huh.
The complete equation, would you do lithium 2 sodium hydroxide plus H2 gas and plus potassium bromide as well, or would you do without the complete?
In the complete equation, the potassium bromide doesn't react. So in the complete equation, if you were to, you could do this. This one's easy to do because nothing. But in the complete equation, technically, you know, you'd end up with potassium bromide on both sides. So one thing you could do is if you have the same thing on both sides, you know, balancing equations, you're supposed to cancel it out. I don't know, the complete, you're supposed to have everything in there, so you probably just leave it in. So this is a spectator. And so that would be the complete equation. And the ionic equation, this is something you guys don't have to do, you recognize. But, you know, some people might get bored or something and want to know something a little bit more. So you could do the ionic equation here. The ionic equation would be sodium solid plus 2H2O liquid plus potassium ions plus bromide ions yields potassium ions, bromide ions, 2 sodium ions, 2 hydroxide ions, and H2 gas. That'll be the ionic equation. Since we end up with a net ionic, that's fine. You could just leave it in terms of net ionic.
Do you need the 2 for the sodium?
On the left, yes, I do. Thanks. It's not balanced, you're right. Thanks for catching that. Okay, any other questions for reactions? Are you making some progress on the homework?
I'm done.
You're done? Good.
Everything.
Everything? Good. If you're uncertain about some of those reactions, you should post it on Piazza or something.
I've been really active on Piazza lately, right?
You have been. That's good. That's good. Yeah, everybody's welcome to ask questions on Piazza.
WRA just because the reaction occurs. Is that true?
Yes. All the, you know, did you notice I'm having you do an extra step? For some of these. You know, when you have a skeleton redox, there's a driving force. There's got to be a driving force, otherwise you wouldn't get any product. And so skeleton redox is a driving force present. And so for skeleton redox, you're going from SOA, SRA to SWOA, WRA. You know, you have to be, because there's a driving force present. And so what you have to do is you have to identify these from the skeleton redox. Well, what's the easiest way of identifying them? Not from the net ionic. The easiest way is from the Zach. The half reactions. Yeah, this we only do the half reactions. And so when you're at the half reactions, before you add them up, that's where you're going to identify it, and then you know it goes from stronger to weaker. Okay. All right. Any other questions on the reactions? You got
Last one, number 6, it is sodium hydrogen carbonate and lithium monohydrogen phosphate. I'm having trouble figuring out what the products with this.
Okay. Sodium hydrogen what? Carbonate and lithium monohydrogen phosphate?
Yeah.
All right. First thing is you have to get the formulas right. If you need to review nomenclature, make sure you review it. Okay. No, this is not directed at you, but directed at everybody, because let me tell you, if you write the wrong formula, you're not going to get much partial credit. For sure. So we have these. And then if we do a metathesis, then we just switch the cations. You know, metathesis is no driving force. Right. Did you try metathesis reaction?
I did, but what happened is it will be NaH2O4.
Yeah. Okay, when you do metathesis, you have to break it into anion and cation. When we break this in, this is the way I look at this. This is the sodium cation with the bicarbonate anion. I don't remove the hydrogen. The hydrogen is part of that anion. And the same thing here. This is lithium cation with the monohydrogen phosphate. Now, for metathesis, we'll just switch partners here. You know, we'll just look at the other ion combination. The other ion combination would be sodium, hydrogen, phosphate. We need 2 of those sodiums, plus lithium bicarbonate. All right, then we'd have to balance this. Since we need 2 of these, we get 2 of these, this. Then it's balanced. Then we look for driving force. Precipitate. No, group 1 salts are soluble, no precipitate. Gas formation, neither of these decompose nor are they gases. Stronger acid to weaker acid, no change. And so what we say is this, we don't say NR, we say NR for metathesis. Just because we don't have a metathesis reaction doesn't mean we don't have a reaction. We might have a reaction. We have to take a look at the other scenarios. What's the other scenario? Well, next we go to Bronsted acid base. If we go to Bronsted acid base, then there's sodium bicarbonate, lithium, monohydrogen phosphate. And water. And then you rank them. You know, what's the strongest? Well, lithium ions and sodium ions are neutral. This is acid and base. Acid and base. Acid and base. So we have 3 acids, 3 bases. Just find the strongest acid. It's the strongest acid present. Bicarbonate. It's the strongest acid. It's the strongest base. Water or hydrogen phosphate? According to the chart, let's take a quick look at the chart here. Strongest base on this chart is amide. Bicarbonate. Bicarbonate's stronger, closer to amide. Water, we don't get the water until way over here. Bicarbonate's stronger, but we already had bicarbonate as the strongest acid. But what about hydrogen phosphate? Monohydrogen phosphate is actually stronger than bicarbonate. So monohydrogen phosphates are base. Acid's a proton donor.
Now, why would now could you consider hydrogen carbonate as your base and HPO4 as your acid?
Yeah, you could. You get no reaction. Is that? You could. You know, these collisions happen. All the collisions will happen, and you get a mix of things happening. But the only thing you have to worry about is, you know, if you're going to consider all these possible collisions, you don't. You just want the one collision with the highest probability, the highest driving force, likely. And the one collision with the highest driving force that's likely that, it's not, you know, the highest driving force may be not strong enough to have reaction, but you pick the strongest. The strongest will react, right?
Third from the bottom, what is that in that water?
The third from the bottom. You're talking about this water here. Yeah, I completely ignored this water. Why? It's on the acid side. This chart has the acids on the left and the bases on the right. This is like, okay, hey, what's the biggest apple? Well, I have this very large orange. I'm gonna give it to you. You know, I wanted the apple, I didn't want the orange. Well, it's the same thing. If you ask somebody, you know, what's the biggest apple? And I say, oh, it's hydrogen phosphate, but you're telling me I missed this orange over here. I missed that orange. And then I'd say, well, we're discussing apples and oranges. I don't want to just talk about apples. And so don't mix the chart up. You got to stay on one side. And so when we look at the bases, we just stay on the base side. I know it's going to occur, and people get it mixed up all the time. But, yeah. So which one loses the proton? Well, both can lose the proton. Which one is more likely to lose the proton? Which one is more likely to lose the protons is stronger. Why? Because it's the one that's going to break off most easily. You know, if a base is trying to plot, like say this guy bicarbonate tries to attack this and pull the proton off. It tries to pull the proton off, but it meets some resistance because it's not a very good acid. This one attacks this one and tries to pull the proton off. Oh, it's much easier to pull the proton off because this is a better acid. The stronger acid will react because it's just easier. So, What forms? What form? This is what confused a lot of people. Well, we have to, I don't know, you have to know what the acid is and what the base is. So we already figured that out. Acid loses the hydrogen. So we have to form carbonate and dihydrogen phosphate. Now going backwards, we look. This must be the base, this must be the acid, because going backwards, we just look who gains, who loses. And then we compare bicarbonate versus dihydrogen phosphate. Well, I don't know, but we can look at the chart. Now, we're comparing two acids, so we gotta stay on the acid side. And so we look at bicarbonate and dihydrogen phosphate. Here's dihydrogen phosphate. Here's bicarbonate. Dihydrogen phosphate is a stronger acid. So this is a stronger acid, this is a weaker acid. And then the bases should follow. So monohydrogen phosphate versus carbonate. So here's carbonate. And so carbonate's stronger. Carbonate's a stronger base, this is a weaker base. Then I go, wow, I must have done something wrong. Because it's always got to be strong, strong to weak, weak, or weak, weak to strong. So I can't have a mix, strong, weak. There must be something wrong.
It says that dihydrogen phosphate is stronger than carbonate.
Oh, okay. Dihydrogen phosphate is stronger. So I must have screwed up the acids here. And so this is weaker, this is stronger. Now it makes sense. Weaker, weaker, stronger, stronger.
But that's no driving force.
Right. So unfortunately, this one has no driving force. When you have something, okay, in Chem 1A we do this. We would just say no reaction, right? If there's no driving force, we do no reaction. This is Chem 1A review. But so we got no metathesis, no acid base. But what the situation is this. The situation is, this is like a seesaw. If one side is much stronger, then it's going to be like this, right?
Yeah.
But if they aren't, one side isn't that much stronger, it's like this. And so this is a scenario where we have both reactions occur. We have a balance. Let's say it's just slightly weaker, then it's going to be like this, right? And so what we have is, this is what we have in equilibrium. We're actually going to have a mix of all these species, and this is what we're going to do in Chem 1B. We're going to do problems like this and figure out how much we have. We're going to do Chem 1A style. We're doing Chem 1A style now to give us an idea of what's going to happen, to see what kinds of reactivity we're going to get. And so we want to get good at this qualitative prediction before we start doing the quantitative stuff, which we're going to be doing later on. So in this particular problem, we're going to revisit this as a very similar problem to this and see how to deal with it. All right, so it looks like we have no reaction for metathesis, no reaction for Bronsted. Lewis, okay, we have a visitor here, so go ahead. I'm gonna pause the video. Or actually, maybe do you want it, is this recorded?
Sure.
All right.
Okay, so hello everybody. Hi Kelly. Hi Oliver. Hi Samar. So, hi. How are you? So, anyway, I am the Chem 1B facilitator this semester. So, we're gonna have the workshops. I don't know if you guys saw on Piazza. I posted it online, an announcement. So you guys are like the 2 people that saw it. Okay. Yeah, it said it only had like 5 views, but I posted it online last night around 9 or so. And I'm gonna be the Chem 1B facilitator. It's gonna be on Tuesdays and Thursdays from 12:30 to 1:55. So I think that conflicts with this class, right?
No. It's just 5 minutes.
It only conflicts for 5 minutes?
Yes, the lab period ends at 12:35.
Oh, okay, then that's not so
No,
bad
no,
then.
our lab ends at 12:35. Yeah, you're right, sorry, 12:35.
On Tuesdays and Thursdays?
Yeah, we're out of this class at 12:35.
Okay, then that's not so bad then. That's not so bad then. So we don't need a Friday session for this class. It'd be useful. Okay, so let me go ahead and get a petition to go around. I know you guys don't have much time yet. Just sign the paper if you believe that you want to have a Friday session, and I'll go ahead and talk to Mesa about it.